The recording is now in progress. So I have to pick back up with lecture, which is fairly ridiculous because the last time we spoke about chemistry was January 27th. It's been a minute. And I have to start talking about these things that we did talk about almost 2 full weeks ago at this point. So it's going to be a little rough as we ease into it. Before I pick up with that part, I wanted to just say on Zoom, since we have a lot of folks who are not here, that overall exam 1 went pretty well. Asterisk. This is going to be the lowest amount of material you're going to see on an exam because we missed 2 full days of lecture plus MLK Day. There was a lot of blank time in here. Exam 2 will not have that same amount of blank time. So if you did well and you feel like, man, I got this, I'm like comfortable, keep doing what you're doing. If you feel like, oh, I just barely snuck in there a little bit, step it up in a big way because exam 2 is going to come in even harder than exam 1. And not because I'm going to come after you guys, but just because the amount of material is going to be more, just because we're going to be talking about more stuff. If exam 1 did not go your way, and for some of us, it was a swing and a miss, do not shelter in place on me. Right? We can run, we can hide, or we can freeze. And most of the time, we'll fight. So there's another one. We can run, fight, or freeze. Most of us freeze whenever we get into a panic situation. Do not do that. If exam 1 didn't go well, make it the last time that an exam does not go well for you. What I mean for that is, on exam 2, get pissed at me, get pissed at the class, get after it, get motivated by this, and make sure that it doesn't happen again. We have lots and lots of points left in class, right? So 1 bad score, if you have a bad score, is not a death knell. It is a knock on the door that says, hi, I'm here to remind you that you need to bring your best to bear. Right? So do that. I am cheering for you. If you have questions about how to bring out the best in yourself, come see me. We can talk about it. I'm very friendly. Yeah. The next quiz is the start of material today through your quizzes on Friday, I think. Yeah, think about for OCHEM 1, this is totally ridiculous. OCHEM 1 had their exam pushed to Friday as well. We had 1 lecture today and they have a quiz on Wednesday. So it's great. Snow days are great. Love them. Many moons ago, way back in January of 23, we were talking about Friedel-Crafts alkylation reactions. And I got into it enough to tell you that there are problems with Friedel-Crafts alkylation reactions. Namely, the ones we know so far are we can't do an alkylation reaction. We have to use alkyl halides, so we're limited there. We can't do alkylations when the benzene ring is substituted with an electron withdrawing group or a basic amino group. Now, picking up with that, as I've been told, maybe at least one of us calls them the red rules, we have more problems. These are, let's see, how do I want to write this? Section 16.3, continued. The last thing in your notes is probably in red if you write in color. Limitations of alkylations. All right, one that we have not seen yet is that when you try and alkylate a benzene ring, remember what we need is benzene as the nucleophile. We also need some sort of alkyl halide. So an example of that would be this molecule. Let's test our OCHEM 1 knowledge. What is the name of, so this is benzene. What's the name of this molecule? Butyl chloride. But where is the chlorine? 1. This is 1 butyl chloride. Well, sorry, no, butyl chloride's fine. We don't need a number for it because we're saying that it's a butyl group. 1 chlorobutane is the other way you'd write that. It is an alkyl halide. What's the other thing I need in a Friedel-Crafts alkylation reaction? Okay, what? I can see you. What'd you say? Catalyst, thank you. Yeah. Thanks for making that so easy. Can you remind me, what catalyst were you catalyst did you wake up with on your heart this morning? FeCl3, love it. Iron trichloride is our catalyst that gets this thing going. We would expect that when this occurs, we would see a benzene ring with 1, 2, 3, 4 carbons hanging off of it. 1, 2, 3, 4. And maybe there would be the other one we brought up is multiple alkyl groups, like polyalkylation is also an issue. We do see this, but we also see this, to which you should all say, what? How in the heck did we make this thing? Who wants to know why? Mohammed wants to know why. You want to know why it forms, don't you? That's your question. What's your other question? Didn't draw this last time? Yeah, this is all new. This is brand new content. Content coming in hot. No, last time I did it, I think I used probably a methyl group and made toluene. Oh, no, I did use T-butyl chloride. That's right. And then made jazz hands. Jazz hands. Yeah. This is a different molecule. That is not T-butyl chloride. That's a bold-faced lie. T-butyl chloride looks like this. All right. So then your other question is, we agree that that's not T-butyl chloride, but your other question was, man, that's crazy. How did you form that? Well, because Mohammed asked, what's going to happen is in that first step, and I'm going to not do everything in red because I need to use arrows to make this. We are going to form a carbocation. So I'm going to skip over a step here. Instead of having chlorine directly attack this iron, which many of you showed quite nicely, I'm going to show that bond breaking to attack the iron. What that's going to give me is FeCl4 minus. And again, many of you did a great job of accounting for all your charges, even the inorganic stuff. Love it. What's going to be left is a carbon with a positive charge over here, a carbocation. What kind of carbocation is this? Primary. How do we feel about primary carbocations? Not good. In fact, they are the least stable carbocation. If only there was a way that that carbocation could move some things around to make itself more stable, but unfortunately there's not, and this is where we're stuck. What? It could resonate if there was maybe a double bond nearby, but there's not. Hydride shift, very good. Next door, we've got carbons with hydrogens on them. They can jump over. I'm going to draw all my hydrogens in here. One of these hydrogens, sorry, I drew this so small. Blow this up just a little bit. One of these hydrogens can jump over that bond, can move over to where that carbocation is. So a hydrogen and 2 electrons, when I draw this arrow, it means the hydrogen and both its electrons move over. So it looks like this. That's called a hydride. Move over to the carbon on the end, and now my positive charge moves here. This is called a hydride. And when a hydride jumps from one carbon to the next, we call it a hydride shift. What kind of carbocation did I make now? Secondary. How do we feel about secondary carbocations? Better. Still not the best, right? Tertiary would be best. Benzoic would be even better than that, but tertiary, secondary is better. It does not go back and forth. So this is a definite one-way street, because for it to go back, I have to break a carbon-hydrogen bond, which is asking a lot, in order to make a product which is much less stable. So what happens is when this carbocation forms, it jumps up in energy pretty high. And the molecule freaks out and says, I don't like the positive charge on this carbon. Can I do anything to alleviate it? It moves a hydrogen and a negative charge over, settles down into a lower energy state, and then reacts from there. You guys with me so far on this positive charge ending up on the primary carbon, jumping over to the secondary carbon? Step 1 is activate the electrophile. What's step 2? on the next episode of When Benzene Attacks. Now we're going to attack the secondary carbon. Wherever the positive charge is, that's where benzene is going to attack. I'm going to stop doing this and put my hydrogen down here. Okay, so here's the part that gets confusing for you guys. The new bond is going to come from here. So I'm going to draw my line here for my new bond. Look at where I attach to this carbon. I'm going to attach 1, 2, 3, 4 carbons, but I'm going to do it at carbon number 2. So I'm going to attach 1, 2, 3, 4 carbons coming off of this. You see how I did that? Maybe if I draw it, actually, let's keep it in the same orientation. So 1, 2, 3, 4. It attacked the secondary carbon. So you got to make that connection over here as well. This is really easy to lose track of. So the mechanism is, I think, very helpful for keeping track of where that carbon bond is formed to benzene. Yes. Yes, he did. And very fortunately, he is not on Zoom. I encouraged him to not be. All right. So now we have our positive charge on here. What is this thing called? The sigma complex. Did you guys learn something and retain it? How do I get rid of that sigma complex? Base is going to come in, take a proton, and reestablish aromaticity. Ooh, that is, now we're really getting fancy. You guys drawing ugly benzenes yet? That's when you know. That is how you make that through a carbocation rearrangement. Now, if you're after rearranging a carbocation, that's great. But if you're not, I put it here as a limitation. Alkyl groups can rearrange. And that's a problem. Would you like to try one? Yeah. Oh, questions? Yeah. Great question. So it's not which one's more stable or more favored. I mean, circle everything. Is anything actually circled? The way you want to ask that question is, which product is your major product? Because they are both equal in stability. It's just one is more likely to form than the other, and it's the rearranged product. The rearranged product represents 65%. This represents 35%, right? So this is what we would expect, but we get less of that in the flask. The reason is, as soon as this carbocation forms, it instantly rearranges. Because what has to happen is, here I have an intermolecular reaction. Benzene is going to attack that carbocation, which means it has to run into it. This is an intramolecular reaction. Once the carbocation forms, it's going to rearrange within itself. It has all the pieces it needs. Someone comes up and pulls my chlorine off. I have a positive charge over here and go, nope. I can do that before you guys can come up and hit me. You're busy. You did. Right, so I'm faster at doing this. I'm not good at blocking. I'm definitely getting punched in the face, which is why I'm not going to do it. But I can move my hydride over very quickly. That's why this is the major product. It's not that it's more stable. Let's try one. Color scheme is just awful there. I'm done writing in red. Thus concludes the red rules. Mohammed, you don't know it yet, but this one is for you. What is the major product of this here reaction? The single major product. Which, by the way, if I don't ask for products, Stop drawing multiple answers. I have to grade everything you put on the page. Stop it. Commit. Want a pro tip on how to not screw these up? You do not need to draw the whole mechanism out. Draw the carbocation that's going to form from that. Have it on the page where you can see it, positive charge there and everything. And think about if you can move that positive charge. And draw that on. You don't have to draw the whole mechanism, but once you see where that positive charge is, that's where then you can connect. Try that. Got something? Just throwing in the towel? What you got, Gabby? What's our initial carbocation going to look like? Uh-huh.
So you're gonna take the, or sorry, yeah.
Uh-huh.
Take that.
It's going to pop off of there, and that's going to make what? Positive charge where? At the top. Okay, what kind of carbocation is that? Primary. We don't like those. No. So what are we going to do about it? I'm going to move a hydrogen up. I agree. I'm just going to make this look like what? In the middle. Very good. What kind of carbocation is that? Tertiary. How do we feel about tertiary carbocations? It's almost Valentine's Day. Tertiary carbocations are the best. Benzene's going to make a connection there, and that's going to look like what, Gabby? Sorry, Mohammed, that's going to look like what? Is the answer jazz hands? We're going to put a tertiary carbon on that benzene. That's one. What's going to happen is this will occur again. So if you just drew this, that's fine. We're going to find out in just a hop, skip, and a jump that we will do this multiple times. So we will get, he's even got a little smirk, jazz hands on there. But if you drew just one, totally fine. You see how that happened? How we turned, I love being over here, but I can't reach. How we turned this alkyl halide into this positive charge. Do this. When I ask you to do these kind of problems on the quiz on Friday, I want you to draw out the carbocation. I want you to show me the carbocation moving, and I want you to show a connection to where that positive charge is. If you screw something up along the way, you can at least show me you know that it's a rearrangement problem. But chances are, if you draw it out step by step, you're not going to screw it up. Note, I did not draw the entire mechanism. Some of you overachievers are drawing the entire mechanism on every question I give you. I have to grade everything you put on the page. Fortunately, you've been doing it right so far, but I encourage you to take a legal approach. Answer the question that is asked. If someone says, were you here the night of blah, 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 don't be like, I was, but I also skipped a parking ticket and blah, blah, blah. Just shut up. Yes, I was there. Right? So if you're asked just for products, draw just products. It's a good idea, but you can give yourself little breadcrumbs along the way. Alejandro. If you drew everything I just drew, yeah. You think I put up crap information up here? What kind of shop do you think I'm running? No, if you put this, you get 50% credit. Just you though, everybody else. Yeah. Yep. We'll come back to that. Why these things are making jazz hands while we're having multiple alkylations, we'll get there. Okay, so Friedel and Crafts came up with this reaction. They were like, oh my God, we made a new carbon-carbon bond. That's fantastic, wunderbar. But then they found all these problems they had with it. And so they developed a similar carbon-carbon bond forming reaction, but it doesn't deal with any of the same limitations. And that is called Friedel-Crafts acylation. That's in red. This is a good reaction. It'll be in black. How could you possibly get these two reactions confused? Alkylation and acylation, two totally different things. They behave very similarly. The Friedel-Crafts acylation reaction is going to use benzene because it is an EAS reaction. Come on, benzene. Okay. Except this time we're going to react it with something called an acid halide. This is an example of an acid halide. It's a carboxylic acid where we replaced an OH with a halogen. Same thing, whatever your halogen is, that's the catalyst you need to match it with. So Fe, we've been using iron for everything, let's use aluminum. Iron trichloride or aluminum trichloride. And what we're going to get is an acyl group on there. And we're going to get only that product. This is 95% of the flask. No limitations, no rearrangement, no polyacylation, just good, clean chemistry. I put two things in the flask. I got one thing out. That's the way we want to be, right? We don't want to make multiple products. Yeah. Typically with NMR. So they'll take a scoop of it and, well, you clean it up first and you can weigh out the materials, but you confirm the materials with NMR or mass spec. Some of those instrumental techniques we talked about at the end of OCHEM 1. Who wants to know how this reaction works? It's so much better. Everyone put their hands in the air. I saw it. First step of all EAS reactions. Activate the electrophile, they all shouted out in joy. This chorus. Yeah, I didn't have enough. There was, yeah, I did. You'll see why. It's fun. Okay, we've shown previously for Friedel-Crafts alkylation reactions. First thing we're going to do is break this carbon halogen bond. We're going to do the same thing here. We're going to graduate though to just go ahead and break the bond instead of trying to mess with the halogen because we got some steps to get through. So step one, bond is going to break to attack the aluminum. AlCl4 minus is going to pop off of there. And I'm going to be left with this weird looking molecule with a positive charge. There was no hydrogen here at that carbon. Why is it okay to make this carbon with a positive charge like that? Can I do anything to stabilize that carbon with a positive charge? Resonate with the oxygen. Right? I can take the electrons from the oxygen and push it down and make this ion. It's the same ion, just a different resonance form. This is called the acylium ion. Because you used a catalyst. You're right, this chlorine's not going anywhere. But when the catalyst runs into the aluminum is like, hey, chlorine, why don't you come this way? Ha, pulls it off the molecule, and then all of a sudden they go, wait, we're unstable. Just long enough for step two. Man, benzenes are really getting out there today. Step two is, of course, when benzene attacks. How am I going to draw this arrow? You'd think to the oxygen, right? The oxygen has a positive charge. If I draw the arrow towards that oxygen, I need to move electrons away from the oxygen, right? So, because it has 8 electrons already, 2, 4, 6, 8. If I attack the oxygen, I'd have to push electrons down to the carbon, which would give me a negatively charged carbon. Let's not do that. So instead, what? Yep. No, onto the carbon, right? So we're going to go from the carbon-carbon double bond onto the oxygen. Because that one's not very stable, this is the better resonance contributor. And you're going to remind me why, Mohammed. Why is this not a very good resonance structure? What about it? How many electrons are on this carbon? I want to hear it. How many? 6 total electrons. How many electrons do we want around carbon? 4 associated. How many total? 8. We want to get to an octet, right? So we have 2, 4, 6 total electrons around this. The carbon has a positive charge because it has 3 associated. This carbon, how many total electrons? Correct. How many total electrons are on this one? Total. 8. How do we feel about 8? Love it. That's why I'm drawing this one. So the benzene's going to attack over here. Sorry, I'll stop picking on you eventually. The carbon attacks over here. It is. This attack is what pushed the electrons on top of the oxygen here. So we have our positive charge over there. Made our sigma complex. Step 3. Base. Reestablish aromaticity. Nah, I need a little more curve to that arrow. Take it to our final product. Which one? This one? That one? This one. That one. That's the reaction arrow. That's the yield arrow. You guys are after me today. This one?
I'm just saying, like on Eagle Road, we die right now.
I agree. You should not drive like you draw arrows. In fact, actually, I think you should really put some autistic flourishes in there. We should all take calligraphy. Please don't. Appreciate y'all. Questions about Friedel-Crafts alkylation, Friedel-Crafts acylation, and why acylation is way, way, way better. Okay. I have been flirting at the idea of putting something on benzene impacts benzene's ability to be a nucleophile and changes the next reactions. This is where we're going to start to take all the reactions that I've shown you, add in a couple more, and then we're going to finish this with a beautiful wedding cake of synthesis. I'm going to, at the end of this chapter, say, here's benzene, and I'm going to have an arrow, and then there's going to be a nightmare on this side with benzene with stuff all over it. And I'm going to say, propose a synthesis. Show me how to get from here to here. It's not just one reaction, it's going to be multiple steps, and the order of those steps matters. So from here on out, I'm going to show you ways you can think about how to synthesize a molecule. This chapter is hugely important because this is how organic synthetic chemists have to think. If you have taken a drug, pharmaceutical prescribed drug, I don't know about the other ones, whoever made that pharmaceutical did this same process. They looked at a map of a molecule and said, how am I going to build this thing step by step? How am I going to put my Legos together to build this? The first consideration for that is section 16.4, which is substituent effects. In electrophilic aromatic substitution. Substituents do a couple different things. Number one, they impact the reactivity of enzymes. Benzene. I've used this word substituent in here.
Yeah.
Maybe my arm, substituent of my body. A substituent is a piece of something. All right, so we can do one of two things. We can have activating groups. Those are going to add electron density. And increase benzene's reactivity. Benzene. Are activating groups going to be electron donating groups or electron withdrawing groups? Donating, because we're adding electron density, right? So we're going to call those EDGs. I brought that up before. We used EWGs, I think. We used EWGs. Let me write these out. So electron donating group is going to be known as EDG. On the other side of this, we can attach groups to benzene that remove electron density. We're going to call those deactivating groups. Those remove electron density from benzene. Let's just say remove electron density and decrease benzene reactivity. These type of groups are going to be electron withdrawing groups. Or EWGs. Step 2 of every electrophilic aromatic substitution is benzene attacks. Benzene must be electron rich to attack. It's going to act as a nucleophile. If I have a group on me that adds electron density to me, I am better at reacting. If I have a group on me that's taking electron density away, I am less likely to send out electron. Right? So if I have a group adding electron density, better at attacking. Removing electron density, worse at attacking. We need to pay attention to what groups are on there. Remember when I had you draw out nitro and I said, hey, that positive charge on the nitrogen really matters? That positive charge on the nitrogen is an electron withdrawing group. It's going to steal electron density from benzene and slow that reaction down tremendously. Let me show you an example of that. If we look at a reaction of a benzene with a group attached. So I'm going to do something a little weird, a group not on any individual benzene, not on any individual carbon. There's an X group on there somewhere on the ring. I'm doing this on purpose because we're also going to talk about directing effects. If I run a nitration reaction, I need HNO3, H2SO4. What I'm going to get is my X group is going to be on there somewhere, and I will attach an NO2 to it. It doesn't matter what reaction I'm going to run. This could be any reaction. What I want to look at is, what does the effect of X have on adding my nitro group to the benzene ring? If X equals NO2, right, so the way you'd read this is nitrobenzene would turn into meta-nitrobenzene or dinitrobenzene, right? So there's a nitro group on there. I'm adding another nitro group to it. The reaction rate is 6 × 10⁻⁸ compared to if I just had X was hydrogen, the reaction rate is 1. So this is reaction rate. So a way to think about this, because I know it's going to be confusing with substitute or with X groups on here. When I have X, X equals hydrogen. Yeah, that's fine. I can keep doing that. When X equals hydrogen, and it's just benzene, if I put a nitro group on benzene, I'm saying that's my standard reaction. Benzene turns into nitrobenzene. Now I want to compare that to nitrobenzene turns into dinitrobenzene. The nitro group on benzene slows that reaction down to a small fraction of the rate of just benzene doing it on its own. Right, so nitro groups withdraw electron density from benzene and prevent it from adding any other group on there, be it nitro or whatever else you want. If I put a chlorine on there, the rate is 0.033. So what does that tell you about chlorine? It's an electron donating group or electron withdrawing group? An electron withdrawing group. Is it as strong of an electron withdrawing group as nitro? No. So if I have benzene, it's going to slow down if I have chlorobenzene that I nitrate. So I'd have chloronitrobenzene, but it's not nearly as slow as if I took nitrobenzene and made dinitrobenzene. That reaction would take forever. If I have a OH on there, the reaction is 1,000 times faster. Phenol nitrates 1,000 times faster than benzene does. I can tell by some of the glazed over looks in your eye that I need to draw this out because I am losing you rapidly. You can. Totally different. I've got two nitration reactions. Right? So on the top, benzene turns into nitrobenzene. On the bottom, phenol turns into para-nitrophenol. This reaction is 1,000 times faster than the top reaction. The OH group accelerates the benzene's ability to act as a nucleophile. You see how to read this chicken scratch I put up here? There. Appreciate that honesty. Okay, so we need to categorize, is something going to add electron density to benzene or remove electron density to benzene? Not today, but by Wednesday, I'll give you a list of how we're going to think about these groups that we've used so far. But for now, just think about if you have a positive charge on benzene, or if you have a positive charge on the group, it's going to remove electron density. If you have lone pairs, it can possibly add electron density to benzene. Step one, we can speed up or slow down benzene's reactivity. Second substituent factor is called directing effects. Sorry. I even walked over there. I was like, I took my time. Substituents impacts the orientation of the reaction. So when I put over there earlier, I had an X group and I didn't want to tell you where it was because it matters where that group is. When you put something on a benzene ring, it has something to say about the next groups that come along. If you're the eldest child in your family, you know what I'm talking about. When that next sibling came along, you're like, wait a minute. I was here first. I get to name this thing because it's going to impact my life negatively. If you're the second sibling like me, you don't care. You're just going to come in and be like, I'm here. I'm in charge now. And my job is to ruin the first group's life. My brother's my best friend, but I did give him a ton of trouble when we were itty bitty. I don't know why I'm talking about that. Let me show you the chemistry of it. When I have an OH on this ring and I do a nitration reaction. And again, I'm just using nitration as a constant here, but I could do any electrophilic aromatic substitution reaction, any of them. This OH could lead to 3 different outcomes. I could put a nitro, so let's put 3 benzene rings up here. Let's phenol on it. What are the 3 different nitro positions I could add? Ortho, right next to it. Meta, kind of next to it, and para on the other side. Well, that sucks Because now I've made 3 possible products, right? We don't like that. We want to make 1 product or as minimal products as possible. Good news, not all of these products form. I will get 50% this one, 50% this one, and straight up none of this one. The OH is going to direct what we call orthopara directing for whatever group I'm going to add after it. In this case, it happens to be a nitro. And I bet you want to know why. And I bet you know that I'm going to tell you why. Because we don't operate that way. I don't just say, here's a thing, know it, see you later. That's what I like about this class. We turn over all the rocks and figure out what's underneath. Bugs mostly, and like leeches and stuff. When you have an electron donating group, I'm going to use, instead of OH, I'm going to use a methyl on here. I'm going to take this 2 different ways. So we'll do our nitration reaction. So I've already activated my nitro group. I've turned it into nitronium. Benzene has attacked it. So now I'm going to draw the sigma complex for each one of these. If the nitro group adds ortho, I would put the nitro group there. Right? Which means my positive charge went here. And those are my double bonds that are left. If my nitro group went meta, it would go here, which means my positive charge went there, and here's my double bonds that are left. So I'm skipping some steps. I'm showing you just step 2. When benzene, I made the nitronium, benzene attacked it. This is what was left behind. You with me? This is the ortho, this is the meta. It doesn't. I'm going to show you why it doesn't. Yeah, this is the why. Otherwise, you'll just know it doesn't form and you won't know why, and your life will not be as rich and full. There's resonance forms I can draw for the sigma complex, right? Many of you drew them dutifully on the exam. So the positive charge doesn't have to be stuck there. It can move over. You know what? Now, yeah, we'll do them one at a time. Are there any other resonance forms I can draw for this molecule? Yeah, I can move it again, right? Do we like all of these resonance forms equally? Or do we have a favorite? Why is the last one favored? Fantastic. We put the positive charge at a specially stable position. Over here, we have a secondary carbocation. Over here, we have a secondary carbocation. In this case, we have a tertiary carbocation. I've used a methyl group because it's most obvious. You're used to seeing more substituted carbocations are more stable. But remember, the reason why they're more stable is this group can add electron density to that position. If this is an electron donating group and alkyl groups are electron donating groups, then putting the positive charge at the foot of the electron donating group is a great idea because that carbon lacks electron density and the electron donating group is providing it directly at its doorstep. Can I draw that type of structure meta? The answer is no, but let's prove it to ourselves. I can move that double bond over here. So that carbocation and that carbocation are the same stability. I can move it one more time. What's that? I mean, I can move it one more time. It's just that it doesn't help me. Secondary carbocation, secondary carbocation, secondary carbocation. It has resonance, but there's no particular benefit to putting the positive charge on any one of these individual structures. The methyl group says, if you put me on a benzene ring and you put the next group ortho to me, and if you use your imagination, para to me, I will reward you by stabilizing the sigma complex. If you put the next group from me meta, I can't help you. So if you want to get me involved, if you want my electron density to speed this reaction up, I need you to send it ortho or para to me, and I will pay you back with the resonance structure that helps. That's why electron donating groups speed up the reaction and they ortho para direct. Stay tuned. What? Wait. No, I still have more time. Someone just texted me, I guess. Does that make sense? Yeah? You guys gonna freak out on me if I do this again for deactivators? JJ is. JJ, you can handle it. Let's do this thing. So electron withdrawing groups. Are the opposite. If I put an electron withdrawing group on a benzene ring, oh wait, sorry. Let's keep this in black. So now I'm using an aldehyde. This is an electron withdrawing group. If I do the same thing where I add a nitro group to it, I can show you this ortho or meta. Ortho, the nitro group would be there. Positive charge would be here. Meta. The nitro would be here. Positive charge would be there. Let's go through our stabilization factors here. If I move this around, I can put the positive charge there, here, or there. Do it one more time. And I'm sorry in advance. I know I'm going horribly fast, but I'm recording it and you can play me at like 0.5 speeds. And you're like, and on the next structure. This will be funnier when you're not stressed out as I'm drawing all these structures. Same thing I did previously. I can put the positive charge here, here, or here. Nowhere where there's a substituent, right? Just secondary, secondary, secondary. This one, though, has a resonance structure, and I'm going to push multiple arrows because you guys are about to rebel / just leave. I can put the positive charge right there. Now, beforehand, I told you that the positive charge on this carbon was especially stable. How do we feel about it now? How you do about this class? Bad. This group is an electron withdrawing group. You put a positive charge next to an electron withdrawing group. The aldehyde is trying to remove electron density, and you just put a positive charge next to it. So we've got a carbon that doesn't have enough electron density with the group trying to pull even more electron density from it. Not good. This is especially unstable. Meta or electron withdrawing groups meta substitute because they destabilize ortho and para. I'm going to leave that there though, because We're fried, and I will bring this back up on Wednesday, a shorter version of this. We have a quiz on Friday, so make sure you stay on top of your homework and action center. I'll see you guys later.